Syntax builds the form we see. Semantics gives it meanings key. Connectives link what minds devise. Quantifiers range through truth and lies. Modus ponens strikes with might. Modus ponens flips the fight. Logic cuts clean, no shallow line. Through the long night, reason shines.
Previously, we introduced the 4 basic rules of inference for statements involving quantifiers. In this section, we will illustrate these rules in greater detail. Let P be an unary predicate, and let C be a constant element in the domain of discourse. If P of C is true, we call C an example. Otherwise, P of C is false, and we call C a counterexample. If P of C is true, then the statement, there exists X, P of X, is also true, by the rule of existential generalization. Similarly, if P of C is false, then not P of C is true. And by existential generalization, so is there exists X, not P of X. But this is precisely the negation of the universal statement for all X, P of X. As a consequence, we see that an example can be used to prove an existential statement, while a counterexample can be used to disprove a universal statement. To develop an intuition, consider the following figure. It proves that there exists a ginger cat, and it disproves that all cats are ginger cats. The minimum of a function is a nice example to illustrate proofs involving quantifiers. Recall that given a real-valued function f from its domain a to R, we call a real number, m, the minimum of f on a, if the following 2 conditions are satisfied simultaneously. First, for all x in a, fx is greater than or equal to m. Second, there exists some x in a such that fx is equal to m. The first condition says indeed the range of f is bounded below by m, while the second condition says the number m itself is in the range of f as well. Our first exercise is to show that the minimum of a function on a set A, given its existence, is unique. To this end, let m1 and m2 be 2 minima. By definition, both m1 and m2 satisfy the 2 conditions that characterize a minimum. We now aim to show that m1 equals m2. Since condition 2 is satisfied, by the rule of existential instantiation, we know that m2 equals f of c for some fresh element c in A. Moreover, since condition 1 is satisfied, by the rule of universal instantiation, we have f of c greater than or equal to m1 for this particular c. As a result, m2 is greater than or equal to m1. A similar argument shows that m1 is greater than or equal to m2. We leave the audience to fill in the details. Consequently, m1 and m2 are identical. Next, consider the function f from R plus to R, where x is mapped to x plus 1 over x. We prove that 2 is a minimum of f. Recall the 2 conditions characterizing a minimum in the definition. This time, we do not have them in our pockets. Rather, it is our mission to prove that they both hold for the real number 2 in our setting. To this end, let C be an arbitrary positive real number. It follows that fc is equal to c plus 1 over c, which is greater than or equal to twice the square root of c multiplying 1 over c, as the arithmetic mean dominates the geometric mean. The latter is precisely 1. We can now deduce by the rule of universal generalization that for all positive real numbers, fx is greater than or equal to 2. Note how, in the estimate of fc, we only use the fact that c is positive, nothing else. This arbitrary choice is essential for the application of the rule of universal generalization. To complete the remaining half of the proof, simply observe that f1 equals 2. As a result, the rule of existential generalization allows us to conclude that there exists a positive real number x, such that fx equals 2. Putting these 2 facts together, we conclude that 2 is a minimum for this function. We hope that you have now developed a basic sense of how proofs involving quantifiers should proceed. In practice, we often have to deal with statements that contain more than one quantifier, which makes things more tricky. A scenario we will encounter in the next section.
信了天生